Hi guys, welcome back to Data Every Day. Today we're looking at a data set of students' academic performance. And basically it's just a bunch of features about a given student. And at the end, if we look at all the columns, you can see there's a class. And if we look into the data, the metadata here, it'll tell us that the class takes on these three values, low, middle, or high. So basically we're going to be predicting how good of a student we have based on these attributes. Alright, so let's get started. I have a new notebook here. You can see I have the task for today. Given data about students' performances in school, let's try to predict whether a given student will have a high, medium, or low grade. And we'll be using a TensorFlow artificial neural network to make our predictions. So I'm going to start by just importing our typical libraries. We have NumPy, Pandas, Plotly, Express for graphing, standard scalar, and train test split for pre-processing. And we will actually make our model with TensorFlow. Alright, so why don't we load in the data using the pandas.readCSV function. We can grab the file path to the CSV file right over here, copy that, paste it in, and then take a look. And it looks like we have a decent number of categorical features, right? Not too many of these are numerical. Just these, I think. I don't see any others. These are the only numerical columns we have. Everything else we'll have to encode ourselves. Shouldn't be a problem, but what we're trying to predict is the class here. This is low, medium, or high, somewhere in there too. Alright, so let's take a look at some preliminary information based using the info method. And looks pretty good in terms of null values. You can see there's 480 rows, and there's 480 non-null values in every one. So let's start pre-processing. And I just like to double check, make sure that we actually don't have any nulls. Sure enough, 0 for every column. So we don't have to worry about dealing with null values. But we will have to definitely encode a lot of this stuff. So let's start encoding. And what I like to do before I start encoding on a data set with a lot of different categorical columns or features, so I like to make two functions. One will be getUniques, that takes in a data frame and a column, actually a list of columns to get the unique values for. And it's going to return a simple dictionary that will map a column name to the list of unique values in that column. So I'm doing a df subcolumn.unique and then turning it into a list. And that's for every column in columns that we specify. Alright, and then we will have another function called getCategorical Columns. This will take in a data frame, and it will simply return a list of every column, so column for a column in df.columns, but only if df.dtype subcolumn equals object. So this is just going to be a list of all the non-numerical columns. And if you see where I'm going with this, we can now call getUniques, pass in data, and then for the columns that we want to find the unique values for, we will call getCategorical Columns. And pass in data here as well. Alright, we take a look, we can see we now have a nice way of visualizing what kind of data is in every one of our categorical features. And let's note that this actually isn't a feature, this is our target column. So I'm just going to write target column equals class. This will allow us to reference it later. Alright, and then I like to divide up all the categorical features into three categories: binary features, ordinal features, and nominal features. Alright, so binaries are features that just take on two values. Ordinal are features that take on more than two values but have some specified order. And nominal features are features that take on more than 2 values, but do not have a specified order. So I'm just going to go through the list and categorize them. So gender is definitely going to be binary, just male or female. Nationality is nominal, because there's no distinguishable order from one to the next, right? So in here, and then place of birth, also nominal, same sort of form of data. Then we have stage ID, which is going to be ordinal, because lower you could say is less than middle school, which is less than high school. So we put that here. Then we have grade ID, also ordinal, follows in order. So we'll put that in here. Section ID. Can't say much about the order here, so I'm just going to put that in nominal. Topic, which will also be nominal. There's no order here. Semester will be binary. Relation, also binary. Parent answering survey, also binary. Parent school satisfaction, also binary. Student absent days, also binary. And class, which is our target column. So now we have properly categorized each of our features, of our categorical features. And so what I'm going to do next is I'm going to specify a few important pieces of information for encoding binary features and ordinal features. And what that's going to look like is I'm going to specify a list of binary positive values. I want to have some control over which one of my values gets encoded as a 1 and the other value that gets encoded as a 0. So this is why I'm going to specify for each one of these which one I want as the positive value, or the 1. So this will map to, like, each element here will map to an element in binary features. So for gender, we have, I'm going to use M as the positive, as per convention. Then semester, it's here. Let's say spring, S is going to be positive, and F will be fall, which will be negative. And relation, we can say father will be positive. Parent answering survey, let's say yes, will be positive. Parent school satisfaction, good will be positive. Student absence days, above 7 will be positive. Okay, so now you can see each one maps to a different column. So later we'll be able to use this and this together to easily encode all of our binary features with a single for loop. Then for the ordinal features, I'm going to specify orderings. I want, again, control over in which order my features are encoded. So I'm going to specify orderings for stage and for grade. So stage ordering is going to be, let me take a look at it. These, right? These are the values we have. And that's already in the order I want. I want lower first, then middle school, then high school. This will be 0, this will be 1, this will be 2. And for grade ordering, this one it's going to take a little more doing because there's a lot of them. Just grab these, paste them in. Then I'm just going to align the indentations here. Okay. So I'm going to put, looks like we're missing, we don't have all the numbers, but we should be fine. I'm just going to put a comma, take this out, put this first, then it'll be 4, then it'll be 5, 6, 7, 8, 9, 10, 11, 12. Okay, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, good. So I'll run that. Now we have this information. Now we can create our encoding functions. And they're pretty simple functions I use. for binary encoding, we'll make a function binary encode. Just going to take in a data frame, a column, and a positive value, which would be these guys. The one that I want to be the 1, and the other value will be a 0. So first I'm going to start by making a copy of the data frame so that I'm not accidentally modifying in place. And I'm actually just going to take this same format and apply it to my other ones. So this would be Ordinal Encode, and this would be one-hot encode for nominal features. And I don't need a positive value, but here I need an ordering, and here I don't need anything. Actually, we could add a prefix. That'd be good. Okay. So, for binary encode, all we're going to do is apply a lambda function to the column of our choosing. So df sub column dot apply lambda x. So this will take in some x, and it will return 1 if x is the positive value, and otherwise it will return 0. And that will just map that function to every element. So anything that, for example, in the parent entering survey, any yes will become 1, any no will become 0, and that's because we specify that yes is the positive value. So if x is positive value, we get 1, otherwise 0. And that's it for binary encode. For ordinal encode, well, actually, I realize I have to actually set it here. Look at that. For ordinal encode, we're going to apply another lambda function, but this time we're going to use our ordering to get the index. So ordering dot index of x, and that's it. Basically, we're going to take our ordering, which will look like this. We're going to find the x, which would be one of these values, let's say middle school. It'll check what is the index of x in our ordering, which here is 0, 1, 2. So 1 is our index, and then it'll just change x to 1, and it'll do that for every x. So lower level will go to 0, middle school will go to 1, high school will go to 2, and that's that. Then for one-hot encode, this one is a little more involved, but let's just take a look at this function if you don't know what it does. If we take here, let me use one of these. Topic. Let's do topic. If we use the pandas.getDummies function on a column, it's going to take all the unique values in the column, right? These are the unique values that it could take on, and it's going to make new columns with them. And then for a given example, the old value will now become a 1 in the column that it was for. So if that makes sense, let me show you data subtopic. You can see the first 4 are all IT, and the last 5 are chemistry, geology, history, history. So over here we have 1s in the IT column, and over here we have a 1 in chemistry, 1 in geology, 1 in geology, 1 in history, 1 in history. Alright, so you get an idea what that does. Then we can just create that. Dummies will be pd.getDummies of the column that we chose. And there's actually something, let me just look this up. Pandas get dummies. There's something here called prefix, which will it will append a string to the data frame column names. So the reason I'm doing this is because if we look over here, we're going to one-hot encode this column and this column. And you can see there's actually duplicate values here. By duplicate, I mean they're shared between the two columns. So if we one-hot encode these separately, we're going to get multiple columns with the same name. And we want to avoid that, right? We don't want 2 Irans and 2 Moroccos. We could say, we can put a prefix at the end or the beginning of the column name to get a 2 separate columns. So we'll just specify the prefix, and then we'll pass it in here, prefix equals prefix. Alright, and then we're going to concatenate, so df is now going to be pandas.concatenate two data frames. One will be our original data frame, and one will be the dummies data frame, and along the column axis. So we're just going to splice the two together, right? We're going to take the regular data frame, create some dummies from a single column, put that here, and then when we're done, we're going to drop that column that we used to generate the dummies in the first place. So df equals df.drop column axis 1. Alright, and that's it. So these are our encoding functions, and we're just going to go ahead and encode now using them. So let's start with the binary ones. So I'm just going to write a for loop for feature and positive value I'm going to zip together the binary features and the binary positive values. So here's binary features, here's binary positive values, and zip will basically just take them. Here, I'll just grab this. Zip will take and turn it to a list so we can see. It'll take one from each and it'll group them into tuples. So when we iterate through this, we can grab both values at once. So for each feature positive value pair in this zip, data will equal binary encode, that's the function we made, and we're going to pass in the feature and the positive value. And that will effectively binary encode all of our features that are binary. So if we look originally, binary still has M and F, and some F and S, and good and bad, and yes and no, and under 7, above 7. When we run this now, and we take a look, they're now 1 and 0, 1 and 0, 1 and 0, 1 and 0, 1, you can't see the zeros, but they're there, and 1 and 0. So that did what we needed. Now we're going to ordinal encode. So data equals ordinal encode data. We have two columns to do this for, stage ID and grade ID, and we've already specified their orderings. So we'll pass in stage ID and stage ordering, and we'll do the same thing but for grade ID and grade ordering. So if we look over here, you can see grade starts grade 4, grade 8, and stage is lower level middle school. If I run this and take a look, stage ID is now 0 and 1, and grade ID is 1, 5. And there's a bunch more in there you just can't see. Alright, that's great. So now we just need to one-hot encode. And I realize we have 4 of these. So what I'm going to do is actually create another list here that's just going to be the prefixes for each of them. So nominal prefixes will just be, for nationality we can say N. For middle school we can, for place of birth we'll just say B. For section ID we'll say S, and for topic we'll say T. Alright. Then we can simply just say data, we'll say for feature and prefix in zip nominal features, nominal prefixes. That's what I called it? Yeah. Data equals one-hot encode data, feature, and prefix. Take a look. You can see now the prefixes have been applied to each unique value. So we will not have here. Why don't I can in the console I'm gonna write panda.setOption max columns will be none. So now we see it has a dot dot dot. Now if we run, we can see all the columns. And you can see we have all these one-hot encoded columns at the end, and even better, you can see we don't have duplicates. We have B Egypt and N Egypt. So this avoids us having two columns called Egypt. Alright, and you'll notice that now everything is in numerical form. Just as we want, everything. So we're ready to train. That is good news. There is actually one last step before, which will just be splitting and scaling the data. So we'll split the data into an X and Y. Y will be data sub, what was it called? Class, right? Well, we don't even need to say class because we have something called target column, which will just get it for us. And X is going to be data.drop target column. Axis equals 1. Alright, now we're going to make a new scalar object, which will be the standard scalar from sklearn. And that's just going to scale all the columns in X to have mean 0 and variance 1. So X equals scalar.fit transform X. And when we're done, we're going to split the X and Y into an X train, X test, Y train, Y test, with the train test split function from sklearn. Pass in X and Y, and we'll specify a train size of, I guess, 80% is probably good. Because we don't have that much data. We want to give it as much as possible to train on. Although it's always at the expense of having less data to evaluate or model on. I think 80 should be good though. So we'll run that. Then we will create training. And we're going to set up a TensorFlow model here. We'll specify inputs will be tf.keras.input. And actually, before I write the shape, let's take a look at the shape of x, x.shape. And you can see we have 55 features. So we'll feed in a feature vector of length 55. And then we'll have two hidden layers. One will be tf.keras.layers.dense with 64 activations, and the activation function will be ReLU. We'll pass in inputs. Then we will do another layer of the same type, but pass in x. And then outputs will be tf.keras.layers.dense. 3, right? We have 3 different classes, M, L, and H. And then we'll pass in x here. Then we'll set up our model. So model equals tf.keras.model. Pass in the inputs and the outputs. Alright, then we'll compile our model. We'll have an atom optimizer. Our loss function will be a sparse categorical cross entropy. And then we'll just use accuracy as our metric. Alright, then we'll specify a batch size and number of epochs. Let's start with 100. And then we're going to store our model's fit history in a variable called history. So this is model.fit x train, y train. So we're training it on the train set. We'll specify a validation split of 20%. And we will specify the batch size as we did above, and the number of epochs as we did above. And I'm just going to turn off verbose mode to not to clutter the notebook too much. Alright, so we'll run this. Oh, what happened? We have cast to float is not supported. It must have been a problem with the loss function? Yes. I didn't include the activation function here. We have to make sure that we're outputting probability estimates. So softmax will convert them to probability estimates. Alright, train, and we're still getting a problem. So I guess that wasn't the issue. Let's just take another look, make sure I have everything right. Accuracy, Miser inputs, outputs. Let me see. I'm just comparing it to what I had before. This is very weird. There shouldn't be a problem here. Whoops. What could the issue be? Let's see. Well, it seems like there's a problem with the cost function, right? I don't know why we'd be having this problem though. Because oh, I know why. Oh no. Look at this. I forgot to encode the label column. It's still M, L, and H. What's it going to do with a bunch of characters? Alright, we need to encode our label column as well. We'll just use Ordinal Encode. So let's specify target ordering will be L, M, H. And then we'll say data equals data sub ordinal encode data target column and target ordering. Alright, now we'll just step. Now you can see class is 1, 0, and 2 in there. Now we'll just step through all these again. Now we'll try training. Alright, now it's working. Sorry about that. Alright, I'm going to make a figure for Plotly Express that's just going to graph on a line plot our model's performance over time. So history.history is going to have the data from all of our epochs, and then the values we want to plot in the y are the loss and val loss from our history.history. Alright, for our labels, we will be mapping the index of the epoch, which will be the epochs, to, we'll call it epoch, and we'll map value to loss. And we'll give it a title. Training and validation loss. Alright, then fig.show. And you can see this is pretty this is good. Our training loss continued to go down, but at some point it started to overfit and our validation loss started to go up because it got really good at memorizing the training data and got worse and worse at generalizing to new unseen data. So it looks like right around here is the best performance, right? The lowest value of val loss. And we can actually check it with the numpy.argmin of history.history sub val loss, and we get 16. So let's go back and let's retrain our model for 16 epochs this time. Alright, now if we plot it, you can see it converges very nicely, no problem. Let's do model.evaluate on the test set, x test, y test. And we end up with an accuracy of about 70%. So that's pretty good. Alright, that's really decent. I think the data is probably very, it's not too bad at predicting students' grades. I don't know. I feel like maybe some more data would be better, like their actual performance in school, because this is sort of like stuff outside of school that's predicting it, right? The topic they're taking has something to do with it, but like number of times they raise their hand is as close as we get, and visited resources is about as close as we get to actually giving a metric of how they're performing in school. But that's pretty good for what we're given. I think yeah, not bad. Alright, I think that wraps up today's video. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell and leave any comments in the section below. I'll see you guys tomorrow. Have a fantastic day.